paper 970241, paper 4, October, November 2023. Right? We stop at question 9. Right? Review through mass defect and nuclear binding energy. These are some of the things that have come out. What is meant by nuclear fusion? Two small nuclei join together to form one larger nucleus. Right? We are asked to draw the graph. It doesn't go to 0. And then this is 50, 56. At that point, 56. There is 250 about here. Right? There's a marking scheme requirement to give you the full 2 mark. Mark X that could represent the nucleus that undergoes alpha decay. Alpha decay is somewhere around here. YY that could represent nucleus undergoing fusion. Fusion is around here. Right? There's a marking scheme how to award you the mark. Nucleus Z undergoes nuclear fission to form strontium-93 and xenon-139 according to the reaction. Table 9.1 shows the binding energy of strontium and xenon. Remember, there's no per nucleon binding energy for strontium and xenon. The fission of 1 mole of Z release 1.77 times 10 to the power 13 joule of energy. Determine the binding energy per nucleon in mega electron volt of Z. Right, for energy for one nucleus. This is the energy for 1 mole. So you divide by number of molecules in 1 mole. To get energy per nucleus, energy for this reaction. Binding energy of Z equals to binding energy of these two minus your binding energy for this one. This one is the energy that's released. So that will give you binding energy of Z. And then this one is more thing to calculate. Number of nucleon of Z. Right? At the top there is your AS work. 93 plus 139 plus 2 neutron minus 1. Okay, is 233. The binding energy per nucleon divided by this is the binding energy. Right, 1 electron volt is 1.6 and 10 to the power 19 joule. Right, this one you want to change to from mega. And 2.33 is there. I keep on changing my okay with that. More challenging now, this calculation.
Yeah.
Right, ultrasound, review through. These are the things that have come out, we have studied before. And then this one, remember that, review through and you have the time absorption coefficient or attenuation coefficient, the same thing. If they ask you to define, you have to write the whole thing, no? Ultrasound and X-ray are both types of wave that are used in medical diagnosis to form images of internal body structure. Complete table 10.1 to state for each type of wave, the method of production of the wave, whether the wave that is detected and used to form the image is a wave that has been absorbed, reflected, transmitted by the internal body structure. Right? Ultrasound, vibration of quartz crystal, reflected wave. X-ray, electron hitting metal target, transmitted. One type of wave passing through tissue, the wave has an 2% of its initial intensity. After passing through 6.2 cm of the tissue, calculate the linear attenuation coefficient mu of the tissue. Right? 32% is 0.72. Okay, take the I naught down there, get that. Then take the ln, you get that. And mu is 0.53. Another type of wave has passed through 0.53 of the same tissue. Calculate the percentage intensity of the wave that is attenuated by the tissue. Fraction transmitted. (0.61). I or I naught is a 0. Basically, this one should be here. This one should be here. Just calculate it out. Okay, fraction transmitted I or I naught is 0.053, 9.3 cm. Percentage attenuated, right? Transmitted is that one. Attenuated is 1 minus the fraction times 100. If you want percentage, 39%. Okay, any comment? If not, let's carry on to the next paper.
Okay. I think the
Yeah.
electricity and the particles, that one is only my weakness lah.
Say again.
The electricity part and the nuclear part, nuclear.
What about that?
I feel like that one is challenging lah.
Sorry, can't hear you.
Yeah, I feel that one is a bit challenging.
Sometimes it's challenging lah. The question are challenging, no doubt. Just do the easiest one first, so. And then do as much as possible you can with the harder one, no? So that hopefully they will give you some marks for the question you have problem with lah. Wrong, they allow you error carry forward lah. Okay, let's go to paper 4, October, November.
What do you mean by error?
42. Found the question paper.
Yeah.
Radiant is common lah. Very popular question to come out circular motion. right? Angles are set at the center of an arc of length because radius, arc length equals radius. The minute hand of a clock revolves at a constant angular speed around the face of a clock, completing one revolution every hour. A small piece of modeling clay, right? That's modeling clay, is attached to the hand with its center of gravity at a distance L from the fixed end of the hand as shown in figure 1.1. Calculate the angular speed of the minute hand, right? Minute hand will take one hour to go one round. Lah. So it's 2 pi over t, 60 times 60. 1 hour is 60 times 60 or 3,600 seconds. So that is 0.0017 radian per second. Usually the first two part is easier. Lah. Then it becomes more challenging when you read the question. During the time of interval 1.40 second, the center of gravity of the piece of modeling clay in figure 1.1 move through a total distance of 0.44 meter. Calculate the angle through which the minute hand move in this time interval. Right, we just calculate this one. Theta. We got problem with how to calculate distance. Distance is just speed times time. Angular speed times the time. Right? This one is the angle that we calculate the speed. And then that is your time. Determine the distance L, arc length, S equals R theta. So R is your L, S over theta, S is 0.44 meter, 0.44 meter, theta is that one, 0.18 meter. Calculate the magnitude of centripetal acceleration for a piece of modeling clay. Right, these are values when calculated from previous question. And A equals R omega, L is your R. And calculate out. Use your answer in C part 3 to explain why the variation with time of the magnitude of the force exerted by the minute hand on the piece of modeling clay is negligible as the minute hand undergoes one full revolution. Right? The acceleration is very small compared to acceleration due to gravity. So the weight will be also very small. Centripetal acceleration is negligible compared with acceleration of free fall. Resultant force is negligible compared with the weight of the modeling clay. So variation is negligible. Right? These are other possible answers that the examiner will accept from the marking scheme. Define gravitational potential at a point. Put down per unit mass in moving the mass from infinity to the point. The moon may be considered to be isolated uniform sphere of mass that, and there is a radius. Calculate the gravitational potential at the surface of the moon. Give your unit for your answer. If you cannot remember, go to the formula sheet. That's a potential on the surface. Use the radius of the Earth. Right? That's your G. That's your M. That's your M. That's your radius. That's your radius. Calculate out. Joule per kilogram. An isolated uniform sphere spherical planet has a gravitational potential at its surface. A particle of mass m is projected vertically upwards from the surface. The particle is given just enough kinetic energy to travel to infinity, infinite distance away from the planet, escaping from the gravitational pull of the planet without any additional work being done on it. Determine the expression in terms of m and find the gravitational potential energy of the particle at the surface of the planet, just m times phi. Show that the speed at which the particle is projected outwards from the surface of the planet is given by conservation of energy. Total energy is potential energy plus kinetic energy. Take this one over and cancel the m off. So far, okay? Any question you want to ask? Okay, you're
So far,
happy.
okay.
You're happy. Let's carry on. Particle is moving upwards at the surface of the moon. Use the answer in A part 2 and the expression in B part 2 to determine the minimum speed of this particle that will result in it escaping the gravitational pull of the moon. Right, that's why we have calculated A part 2 and B part 2. Then we just put inside this one inside here and calculate out using calculator. And hydrogen gas, assumed to be ideal gas, has a mass of molecule given by their value. Calculate the root mean square speed of hydrogen molecule in the hydrogen gas that has a temperature of 400 Kelvin. Remember this formula? Kinetic energy is 3/2 kT. Root mean square of that one there. Put in your value. This is your 3, this is your K, this is your temperature, this is your mass. Okay. Surface the moon reaches a temperature of approximately 400 Kelvin when in direct sunlight. Use the answer in C and D to suggest reason why the moon does not have an atmosphere consistent of hydrogen. Okay, these are the values that we have calculated. This is the escape velocity. This is the mean so-called mean value of the speed of the molecules. So root mean square speed is an average. So many molecules have speed greater than the escape velocity. Right? So we will be able to escape. Okay, these are alternative answer. Right? These are ideal gas that you have gone through. So if you have time, review through it. State what is meant by internal energy of a system. Sum of potential and kinetic energy of the particles. Total energy of random motion of particles. Use the first law of thermodynamics to explain what happened to the internal energy of a spring when it is stretched at constant temperature within its elastic limit. That's your first law. Right? This one, no thermal energy transfer. You are just stretching it at constant temperature. Work done on the spring increases the potential energy of the molecule. You just separate the molecule, so work done increase the potential energy. So internal energy increases. A sample of water when evaporates from a rain puddle on a hot day. Right? There's the first law. Thermal energy transfer to the water. To evaporate, you must have thermal energy given to the water. Work done by water expanding against atmospheric pressure. That's work done. More thermal energy transfer than work done, so internal energy increases. Right? So we are just doing that one there, and energy transfer to the water. outside the environment. Electron in a metal rod move with randomly about a mean position. When an alternating voltage is applied to the end of the rod, the mean position can be considered to oscillate with simple harmonic motion along the axis of the rod. Figure 4.1 shows the variation with time t of the displacement x of the mean position from fixed point and the axis of the rod. If you should have question you want to ask, one or two, you just let me know. I can help you. If you have any uncertainty before the exam, determine the amplitude of the oscillation. Where's the rest position? That's the rest position. So that's the amplitude. Either you read from here or here. 0.36 and 10 to the power minus 15 meter. Determine the angular speed. That's a period. That's a period. Okay. Use the answer in A part 1 and A part 2 to show that the maximum tree velocity, basically getting you to use the formula, find the maximum velocity. That one we have calculated amplitude, angular velocity, we have calculated. Then V naught equals X naught over times omega. Right? This amplitude is omega. Using a calculator. The rod has a cross-sectional area of 4.3 cm square, contains number, density of conduction electron, charge carrier as a pair. All of the conduction electron in the rod may be assumed to be conservative in phase with and with the same amplitude as the oscillation in figure 4.1. Use the information in A part 3 to calculate the I naught of the maximum current in the rod. Okay. This is your AS code. I naught NQA times V. So that is your N. That's your N. That's your Q, electron, charge on electron. That's your area. Area, change it to SI unit. And there's your speed. That's your speed. Using your calculator to calculate out. And you draw. Right? Remember your speed and displacement is 180 degrees out of phase. Right? This one is right? This one is inverted sine curve. So this is a distance. You are I naught is basically speed. So it's a cos graph. Right? Period is important. That's a period important there. But I don't think they will mark you down even if you invert this one. Okay. Use your answer in A part 2 and B part 1. Determine the expression in terms of I in terms of T, where I is ampere, T is in second. Right? That's your omega. That's your I naught. General equation is I naught cos omega T. I naught 10 to the power 7. Determine the root mean square current in the rod. Right? There's a peak current that we have calculated. mean square is just take root 2, 0.45 ampere. Take Coulomb's law. Electric force is directly proportional product of charges. Electric force between point charges is inversely proportional to the square of their separation. You can combine the two together. That's how they will look for in your mark, in giving you the mark. Two identical oil drops are in vacuum. The centers of oil drop are distant of 0.3.8 times 10 to the power minus 6 meter apart. The oil drops are equal charge and exert an electric force on each other of magnitude 6.3 times 10 to the power minus 17 Newton. Determine the magnitude of the charge on the oil drop. Getting you used to use the formula, Coulomb's law. Right? This one, the two value of Q are the same. So it's Q squared. The square root, cross multiply that, put in your value, use your calculator as your value, 3.2 times 10 to the power minus 19 Coulomb. One of the oil drop is now placed between two horizontal metal plates as shown in figure 5.1. The potential difference of 1200 volt is applied between the plate. With the top plate at a higher potential, the oil drop is stationary and it's in equilibrium. State the sign of the oil drop on the oil drop. Okay, the weight will go down. How to reason it out? For equilibrium, there must be a force going up. So for the electric force to go upwards, the oil drop must have a negative charge. It's attracted to the positive plate. On figure 5.1, draw 4 lines to represent the electric field between the plate. Okay, equal distance from the top to the bottom, evenly spaced. Distance between the plate is 5.2 cm. Determine the mass of the oil drop. Electric field strength. This one divided by, change it to SI unit, cm to meter. Calculate out. And electric force is EQ. Right? And so E. Q is we have calculated 2.2 times 10 to the power minus 19 Coulomb. Calculate out. For equilibrium, F equals mg. M is F over M over G. Okay, 10 minutes left. Right, that's your F. That's your G. Calculate out. Okay, so far? Okay, let's carry on then. The capacitor is charged so that the potential difference V across the terminal is 8 volt. The capacitor is connected into the circuit of figure 6.1. Right? Initially is charged to 8 volt. The switch is initially open. The switch is closed at time t equals 0. Figure 6.2 shows a variation in V with the charge Q on the plate of capacitor as the capacitor discharges. Okay, as the capacitor discharges, the charges on the plate, the potential difference across the plate, show that the energy stored in the plate is quite common now. Remember the formula, E is half QV. Can take any point. Can take any point Q, any point V. right? But usually I prefer to take at the end there lah, easier to read lah. There's 8 already. This one is 450. Right? Remember to convert to SI unit. Check the unit carefully. Don't lose mark because of all that.
Okay.
Determine the capacitance. Okay. Q over V. Then this is your graph. Show that when t equals to time constant, the value of this one is 1. So that's your formula. Rewrite that. Take the V naught down. So we got ln. Right? This negative you can take to the other side. So we got that. There's the equation of this graph. So where t equals RC, n equals to 1. That's what we are asked to show. Determine the time constant t of the circuit. Right? Just read 1. 1, and then your time constant. 3.2. When you calculate, can calculate out. T equals to 1. And this is your RC equals to 1. So RC equals to 3.2. Calculate the resistance. Right? C we have calculated. This is your time constant equals RC. R is tau over C. Put in your value and calculate out. A probe containing a thin slice of semiconducting material is placed in a uniform magnetic field of flux density B. The largest faces of the slice are perpendicular to the magnetic field as shown in figure 7.1. Thickness X of the slice is 1.8. Right? Remember, there's your thickness. Thickness is always parallel to the magnetic field on this side. Right? That's your thickness X. Number density of the charge carrier in the semiconductor is given. The current is given. Pass through the slice between the shaded surface. The Hall voltage is developed between the terminal P and Q. All the 4 surfaces are the current, 1 surface, the field passing through this surface. So the Hall voltage is across the other surface. Right? There are 6 surfaces in the rectangle. Thickness is given. Number density is given. Current is given. Pass through the slice between the shaded faces. The Hall voltage is developed between the terminal PQ as recorded in figure. Figure 7 shows the variation with time t of B. Show that B equals to this one. The magnitude of Hall voltage is 5 volt. Right, go to the question paper, to the formula sheet. Hall voltage is given you. So Hall voltage, put in your value of B. Right, that's your B. That's your Hall voltage. Sorry, that's your 5.4. Current 5.4. N, that's your N. Then it's the electron, so it's charged on electron. Then T, thickness, change it to meter. Calculate out 5.0 volt. We are interested to draw graph, so we have to be careful about the timing. On figure 7.3, sketch the variation of Hall voltage at time t equals 0 to time 0.08 second. Right? It's the same. It's except magnitude different, that's all. Hall voltage and magnetic field are proportional to each other. Right? It follows the same shape, except magnitude is different, that's all. But we have calculated 5 volt. So remember that distance, that flat part, and this flat part there, horizontal part, right? 5 volt. Okay, it's the same, except magnitude different, that's all. There's a marking scheme. How they will award you the mark. All prop is replaced with a small flat coil that has 3,000 turns. The cross-sectional area is given. The plane of the coil is perpendicular to the magnetic field. The electromotive force induced between the terminal of the coil is recorded as B varies as shown in figure 7.2. Show that the magnitude E at the time 0.01 second is 2.0 times 10 to the power minus 4 volt. Use a formula. Flux BA, flux linkage BAN. So AN is constant, so it's a slope, right? That's slope. And the gradient, that's your A, that's your N, 3,000. That's your slope, right? Divided by 0.02. So that's how we have shown. Right, 1 minute left. On figure 7.4, sketch the variation of EMF, E. Right. So that one will be constant. This is 0, right? The slope is 0. Same slope, but different sign. This one is also 0. Right? That's how the marking scheme is. This one doesn't matter. It can be down there, this one up there, but magnitude must be the same. Right? This part is 0. Right? With particle duty, we will review that. These are the formulas you need to remember. Photoelectricity. Anytime will cut off lah. So all the best to you lah. Got question, you can still have a Zoom session with me lah.
Okay.